Welcome back. It's August already. That's... Damn it. Why does that keep happening? Whatever, I guess we all won't have to deal with that for much longer. So this lecture is pretty jam-packed, actually. It's good when I have the folder full of printed out code here. I'm not going to go farther ahead with any other lectures today because the one after this, the second last lecture of the course, requires some pretty extensive preparation on my part. You'll see why later. But then the lecture after that is just exam review. So I think that I don't want to make any promises so as to not make you all too excited quite yet, but we are almost certainly not going to use the entire next week of lectures. The last day of classes will probably be Tuesday or Wednesday. So not only am I going to write some code, you're going to read some code. Yeah, I'm writing, you're reading. There's one genome.c that I'm going to run and demonstrate on my end, but then search.java, that's going to be entirely on your end. You're just reading that. And actually, I think I made a typo. I didn't mean to say genome. I meant to say game. Just check the UMLearn site and download the two files. So today we're going to keep talking about optimization, specifically space optimization, and modularity. I've been saying for a few lectures in a row now that there's some interesting stuff that we're about to get to. This is when it happens. We're going to look at some pretty silly space optimization stuff and discuss why this may or may not be a good idea. Actually, I shouldn't type it up too much. That'll also be some stuff coming soon in the next lecture. But then this other learning outcome about modularity and coupling and cohesion, it's been in the last few lectures but never actually mentioned. We're actually going to talk about that today. This one's irrelevant. Ignore it. But it will be relevant next week. So we left off last lecture talking about the consequences of compression. It's a very useful technique that you see everywhere. It's the reason the lecture recordings aren't several terabytes large, but we're not getting that for free, aren't we? Basically, it takes time and energy. Energy, especially, can refer to either energy as in what the computer is taking up, as well as human energy, how long it takes to make something. A unfortunately very common decision nowadays, which you can see by a bunch of popular apps just being 3 Chromium instances in a trench coat, is that sometimes it's just not worth the developer time and energy to implement meaningful optimizations. And sometimes it's too stressful on the computer. A neat example of this is how PlayStation and Xbox games nowadays can easily be in excess of 100 gigabytes. That's because the developers have weighed the pros and cons of compression, especially for audio, and decided that it's better to leave that uncompressed, even though they know about state-of-the-art compression algorithms. They decided to leave that uncompressed for the sake of faster loading times at the cost of storage. So like next time you buy a PlayStation or Xbox game and it takes up 100 gigabytes of space on its hard drive SSD, probably SSDs for the latest generation. I don't keep up with them. It's probably like 90% uncompressed audio. And textures. Textures take up a ton of space too. So we're going to talk about optimization techniques that really don't cost much computational energy, but may be impractical in terms of human energy, brain power. We're going to talk about manipulating bits. So everything's a number, as you know. And what are all numbers made of as far as computers are concerned? 2 numbers, 1 and 0. And C has, well, I don't want to say all languages, but pretty much all languages have mechanisms for manipulating the bits of a number. And one thing that we need to know right off the bat is that any bit manipulation should be done with unsigned variables. We've talked a little about these before, but basically, unsigned values just can't be negative. They're always positive or 0. As a benefit, you get bigger numbers. Instead of using up half your range for negative numbers, that exponent increases by 1, so you get double the positive values. But more importantly, they have some properties that'll prevent some headaches when manipulating bits. Overflow is actually defined for unsigned values. For signed values, if you go above the upper limit, they usually underflow, overflow, whatever, overflow in this case, into the smallest possible value, way into the negatives. But it's technically not part of the standard. It's undefined behavior. Might cause a segmentation fault on different platforms, who knows? But unsigned values actually have defined behavior. They go to 0. And then most importantly is some stuff that is better explained in a computer systems course. Basically, the way that unsigned and signed values are represented is slightly different, and there are some bit manipulation operations that don't work, or at least might not work the way you intend them to on negative values. I can't go into much more detail because I can't guarantee that you know about like 2's complement and stuff. So just take my word for it. If we keep getting jump scared by this, I might just turn it off and raise my voice. I don't know. Anyway. When you manipulate bits in a single variable, we use a technique called bit masking, using bitwise logical operators. Yeah, screw it. If I'm talking too quietly, just let me know. So the first few operators here, AND, OR, and XOR, use similar logic rules that you've learned about in Math 1240, or perhaps even an intro philosophy course if you've taken one. We can isolate specific bits by taking the number or the variable that we want specific bits of, and then using one of these operators with a mask, a number that's just full of ones or zeros, except for in a specific index. And that'll produce a result with all zeros except for that bit. It'll be much clearer with an example later in the lecture. And then there are a few more bitwise operators that are good to know about and much easier to explain without deferring to logical stuff. That tilde, the unary ones complement, just flips the bits. Every 1 becomes a 0 and every 0 becomes a 1. Shift left moves every bit to the left, and shift right shifts everything to the right. Notably, shift right is one of the operators that makes up an exception to, no, not an exception. The reason why we're using unsigned values, shift right on negative values might not get the results you expect. So we're going to have an example of masking by encoding color the way that it is on the Game Boy Advance. So on that platform, it's encoded in a single unsigned variable, whereas in a more modern platform, they might be, or it's much more likely to be like a 3D vector or whatever word your language uses for collection of stuff. Might be an array, might be a list, might be a collection. But it probably wastes a lot of space doing that, and it's a worthwhile trade-off on modern platforms for the sake of developer ease of use, but they didn't have that luxury in the GBA days. So let's make purple. This is one of the examples where you might want to code along. I'm going to be writing code rather than just walking you through it. And yeah, I can't really come up with a good justification for why we're doing this. It's going to be on the test, but this is kind of just for fun and because it's in the curriculum. Although something of a justification is that if you're going to work on something close to the hardware, so say operating systems, game development, networking, maybe if it's really specialized, then in that case, you're going to do bit manipulation all the time, even on modern platforms. But if you're not, bear with me, it'll be on the exam and we're just going to goof off with really old video game platforms. Just going to give a moment for anyone following along to catch up. We're just doing the usual thing of going to our Comp2160 directory and making a new directory for our example. Guess it's been a while since I've coded live like this. We're going to just do the usual of including stdio.h for output, stdlib.h for a few different reasons. stdlib isn't very cohesive. And a new one. std int standard integer, weren't they already pretty standard? Well, they're not. I hope you remember that table of values earlier in the course that showed how much size or how many bytes different types take up, and int was like at least 16 bits or something like that, 4 bytes. That won't always fly when we're doing bit manipulation. I shouldn't say it won't always fly. That's very risky when doing bit manipulation. We want to guarantee that our numbers are going to take up a certain amount of space, that they're going to be composed of a certain number of bytes. And that's what the types contained in stdint.h will do for us. So we want a 16-bit integer this time. If we were willing to make some brazen assumptions about our platform, or even if we were developing for one specific platform, you could use int, but we're better than that. We're going to use uint16t. uint. There we go. Unsigned integer, 16-bit, and then that underscore t at the end, that's just something that seems to appear often. It's a suffix that basically means type. I don't know why they put that there because it's pretty obvious from context that it's a type, but it's very likely to avoid name collision with things that aren't types. Then we're going to use 8-bit integers for each component of the color. Actually, I'm going to use the full names for better readability. So the color purple is roughly 21 red, 0 green, and 25 blue. Let's see here. With 5 bits per component color or primary color, that gives us up to values up to 32 for each component value, so it's pretty red and pretty blue, but not at all green. Now it's time to get silly, where this line is going to be really dense. First of all, the bitwise operations have shortcuts similar to the ones you're used to. Just like you could do plus equals to do something plus some other value. We could do or equals to make it do the bitwise or with something else. So what the heck did we just do here? We took, actually I'm going to fire up the document camera to help explain this. You may have seen this notation before. We sometimes put a subscript number to denote what base something is in. So blue is 25 in base 10. And then what's that in binary? No clue. Yeah, pro tip, on pretty much every built-in calculator app on each desktop operating system, there's a programmer calculator, and it'll be super useful in Comp 2280 and other systems-themed courses like computer organization and operating systems. So we're in base 10 to 5. So that's 19 in hexadecimal. But more importantly, in binary, it's this. And we add leading zeros sort of as a convention to make it fit within the word size that we're using. In this case, we're working with 8-bit integers, so the word size is 8. So here's what that blue and 0x1f operation is doing. We take the value of blue or the binary value of blue and the binary value of the hexadecimal magic number 0x1f, which really should be a constant. Its usage isn't immediately obvious in the code, but that is a mask that we use to get the last 5 bits of a number. And then this is just like grade school arithmetic. We go digit by digit. 1 and 1, both bits are true. So the result is true. And of course, this works just like Booleans. 0 is true, anything other than 0. 0 is false. Everything other than 0 is true. 0 and 1, false and true. False, 0. Same there. 1 and 1, true. True. 0 and 0 goes to 0. This didn't modify blue at all. So why did we do this? Because each component color is 5 bits. We used that mask to extract the last 5 bits of the number. And that's sort of just a safety measure, just in case we entered a blue value like 1,000 or whatever. Doing that AND with 0x1f extracts the last 5 bits and prevents us from messing up the final result when we do bit shifts. And then the other part of that is this part, which shifts the result to the left by 10. Oops. And remember, we're working with a 16-bit integer for the color variable. So the compiler is smart enough to know that the result of this operation should also be 16 bits. And I think that'll look something like this. Ta-da! Did I do that right? 1, 2, 3. Sure didn't. Oh, yeah. I redundantly added the leading zeros while eyeballing where the bits should go, but I shouldn't have done that. Okay, this time I know that there are 8 plus 2, which is 10, trailing zeros, so I did that bit shift, right? And what was the point of that? Well, now we have our blue component of our 16-bit color. We had here that the bits representing the blue color are supposed to be the, I want to say first 5 bits, the first 5 meaningful bits. This question mark just denotes a bit that gets ignored. So the first 5 meaningful bits of the 16-bit color encode blue. And that's exactly what we've done so far with this, where these bits represent blue. If we finished here, that would be a color that was 25 blue out of 32 and 0 red and green, so a pretty saturated blue color, considering the max for any component is 32 bits. And then we're going to do the exact same with our other color components. But first, I'm going to make that 0x1f a constant because it's easy and magic numbers are annoying. Now we're using bitwise OR to essentially combine the green part with the blue part. And to get the green part, we use the same procedure that we did for blue. We AND it with the bit mask to get the last 5 bits. And then we shift it to the left but by less, we don't shift it as much, in order to put it where the green bits are supposed to be. So we shift it by 5. I'm going to turn back to the document camera. I'm not going to go through this entire process again for green. In fact, it would be really dumb because green is 0. I'm going to do this with red instead. I want to show off the effects of these OR operators, but doing something OR a bunch of zeros won't be very interesting or even possible to tell what's going on.
I don't know if you mentioned this, but can we not make a 5-bit number? Like for red, green, blue?
Yeah, so I didn't mention that, and that's a really good question. A 5-bit type might exist in some header file, but it's very unlikely that it does because these sizes tend to be powers of 2. Which in turn is because computers work in binary, and then the size of the smallest thing that a computer can address just tends to grow in powers of 2 to go along with that. So we just use the smallest power of 2 that's greater than the number of bits we want to store. And also for red, we don't do any bit shifting because the red bits are supposed to go at the end, which is really convenient because then I won't have to do any more bit shifting in my head for the example. I'm going to stay with 0x1f for consistency, but remember that's just bit mask. I could probably do the binary subtraction to figure out what 21 is, but I'm not going to take any chances. I'll just use the calculator. But I don't have to yet. So color so far looks like this. And then let's see what red looks like. So we start with 21, plug that into our trusty calculator. So that's 15 in hexadecimal. And a bunch of alternating zeros and ones in binary. Just like bitwise AND, we do bitwise OR by applying the logical OR operation to each digit. 0 OR 1 is 1. 0 OR 0 is 0. 1, 0, 1, 0, 0, 0. These are probably the green bits. 1, 0, 0, 1, 1, 0. So effectively, that sort of overlaid the two numbers together, whereas and you could think of that as being used to isolate specific bits. So the result is this number, which successfully encodes those red and blue components, and technically the green component because that was just 0. I'm going to attempt to look up something real quick. I just thought of this. Cool. In Comp 4550, real-time systems, you have to do these operations a lot because the hardware that you're using has a bunch of specific registers where each bit of those registers, and if you don't know what a register is, you could think of it as like a global variable. Each bit of the register is meaningful. This bit says whether interrupts are enabled. Anything I could easily explain? These ones seem to be set by other operations, and then you could read those bits using an AND operation to isolate them in order to see some properties of recent arithmetic results. So the reason that I'm showing you this is to attempt to justify that all this bit silliness is still used in the modern world. We no longer have to encode colors using 16 bits because we're better than that. But if you want to work on embedded systems, you're going to do this a lot, and take my word for it that it's also used a bunch in operating systems and networks. I don't know why I did that. We're done with this example, but put on your seatbelts. We're going to do another example. And luckily, this is just going to be me showing you some code. We're going to implement a pretty simple, or I'm going to show you the implementation of a pretty simple lossless compression algorithm. Actually, wait, I'm going to write the return statement and attempt to run this code. This part demonstrates that there are yet more formatting options for printf to print hexadecimal numbers. We'll see what this does soon. If this has many errors, we're probably just going to move on. But it doesn't. Ta-da! The color is hex 6415. 6415. Using the eyeballing it method, we can see that 6415 is the number that we got from all those bitwise operations. Didn't I put this somewhere? Oh, right. I just called it Lecture 21. Now, I am totally out of my element here. I've never taken a biology course in my life, but word on the street is that genomes are encoded using strings consisting of where each character is one of 4 values, A, C, T, or G, which we have encoded here. This string representation actually wastes a ton of space. Every one of those letters is a char, which it depends on your platform, but it probably takes 8 bits. And just eyeballing that looks like 16 chars. Nailed it. 128 bits to store a genome, not counting the null terminator at the end of the string. That's probably not that bad. This is probably a toy example, but I'm not a biologist. I can see there being a situation where an actual biologist doing actual biology needs to store massive amounts of genetic data and would actually care about reducing the file size of the files they're working on. We're going to compress it into 4 chars. So take up just 32 bits. That's a quarter of the space. So again, if you're a real biologist doing real biology and you have like gigabytes or even terabytes of genetic data, crunching stuff down by 75%, making the data a quarter as large as it was, could be insanely useful. I hope. I don't actually know whether biologists work with genetic data in such quantities as to have gigabytes of it. But let's see how it works. This is basically the same bit manipulation as the GBA example, except more complicated. We have some familiar patterns, a bit mask. I believe that's getting 3 bits at a time. And then shifting it by different amounts to put the resulting bits in different places in the corresponding in the binary digit, sorry, the char that we're using to store everything. Okay, I think these bit masks are actually to get specific 2 bits of an integer, of a character, which makes sense because we have those 4 letters that make up genetic data. Don't remember what they are. A, C, T, and G. So that we need to encode it in a way that where each symbol has 4 possibilities, which is a lot less than the 200-ish possible char values that there are. So instead of using 8 bits to store what's essentially a value from 1 to 4, we could do that with, drat, it is 3. No? Yeah. However many bits it takes to store 0 to 3. I'm getting off by 1 errors in my head up the wazoo. Decompress does the same thing except backwards. Notice that we're bit shifting. Why is it recording? Get out of here, Bim. Notice that we're using right shift, which is one of the operators that works differently for signed and unsigned variables. I'll do a quick demonstration on the document camera. Say you have a 4-bit number. No. And you want to shift it to the right by 1. In an unsigned operation, that puts zeros at the start. Or that puts, yeah, zeros at the start, that was fine. Every bit gets shifted right by 1, so the 1 will go to the 2nd bit, 0 to the 3rd, and 1 to the 4th. Whereas the signed number, signed version of this operation, will put leading 1s because there's a 1 at the start. That's it. I don't know enough about bit shifting to know why it does that, but I think it must be something to do with preserving the sign, because in typical integer representations, you could tell the sign of an integer, whether it's positive or negative, by the first bit. And for reasons I don't completely understand, the people who defined the right shift operation wanted to make it so a negative number right shifted stays negative. If that were how it worked for everything, or should I say, if we used signed variables for this, that would result in 1s where we don't want them to be when we do these right shifts. Yeah, so the for loop just takes 4 letters at a time. Decompress goes from the bits to chars, and compress goes from chars to bits. And we can see the conversion happening here too. Then our main line, simple enough, shows the original genome that we're compressing, the compressed one. And then to decompress it, just to prove that we're not just printing the same thing twice, we can't really prove anything here, to better demonstrate that we are, the algorithm to go from bits uses lowercase letters. It doesn't really matter which you use. This is just to show off that we're not just copying the original string, we're actually doing some operations on it. So let's run it. Yay. So we took something that was 16 bytes and turned it into 4. Each of these numbers, or chars, whatever you want to call them, encode the information for 4 letters each, which is a pretty neat example of finding a situation where you're wasting space using an 8-bit, 8-bit char to store just one of 4 values, and then only using the space that you need, just using 2 bits per value to store each of those one of 4 values. So now we're done playing with bits, and for the last activity in this lecture, you're going to look at some code samples and judge them. The samples are on the course website. I'm going to do a Mentimeter so you could submit your opinions. But you're going to judge how cohesive it is. Does it make sense for these things to be put together? And whether it's tightly or loosely coupled. So every piece of code that's complex enough to be worth using depends on something. What's the nature of these dependencies? Does the stuff in the code need to know a lot about the things it depends on to work? Or can we easily switch out implementations of those things and let them still work? I don't think that third bullet point is ever explicitly addressed anywhere, but I encourage you to think about it. This is design stuff that's pre-software engineering, aka useful. So think about how you could change those code samples to reduce coupling and increase cohesion. Guess it's worth demonstrating. Week 5, lecture 21, search.java and game.c. We're going to judge search.java first. And this is kind of a bad example to start out with. It's a bit of a trick question because, actually I don't want to reveal it yet. Basically, don't feel bad if you don't feel like you understand the question. Is search.java cohesive? Do your best to answer after reading the code for a while. And I'm actually just going to kick my feet up. I don't really have much to do during this segment. Put your hand up if you have any questions. Aha, we have an answer saying that it's not cohesive at all. Is that one I agree with, one I disagree with? I'm not going to tell you yet. Keep answering, and I'll offer my thoughts once there are a couple more answers. Someone thinks it's a little cohesive. It's pretty good, but it's not. Wait, by saying that, I didn't mean that search.java is objectively not highly cohesive. I said, but it's not, because the little blue thing shifted to the left as I was talking. Do not let my opinions color your responses. Now it might be a little cohesive. And now I think we're going to move on from this part. So I see most people seem to strongly disagree, but there are outliers. This kind of looks like half of a normal distribution. And what would I say? I just want to refresh my memory first. I'm going to open this in Vim in order to show off a trick. This is one that I use all the time. So say I want to cd to a specific directory, but it's like buried deep within my file system. Actually, honestly, this file path isn't that bad, but I still want to demonstrate it. I could do cd and then just drag the file into the terminal, and it'll be interpreted as a path. Of course, we can't cd to a file, so we can either just backspace through that, or cd, and then I don't know why it's designed like this. Feels a little obtuse, but if you hover over the folder name, a little folder icon appears, which you can then drag into the terminal to get the path to it. A similar trick exists on Windows. In the File Explorer, you can go up to that path bar that looks like a URL bar from a browser up top and just type cmd to open a command window at that folder. And Linux, I don't know, there are way too many different file managers for Linux for me to give the Linux version of that tip. Plus, I don't use any of them. So search.java might have looked familiar. It's that example of bad performance due to bad data structure choices from last class. So is it cohesive? What did I mean when I said that it was kind of a trick question? Well, we can't really judge it because it only really does one thing. It checks whether a collection of words is in the dictionary. That's what it does, right? It checks whether hello is in the dictionary. Fine. We don't have enough information to say whether this is cohesive. it does adhere nicely to the single responsibility principle. It does one thing. Wouldn't necessarily say it does it well, but it does one thing. You would have to judge it by what else it's included with in order to call it cohesive or incohesive. Be warned, the other example, game.c, is also just one file, but it's not a trick question. Ooh. Now, what about coupling? First off, what is search.java coupled with? What does it depend on? And does it have higher tight coupling or lower loose coupling? Think about what would happen if you were to change anything about those dependencies, anything about the mostly implementation, but you could also imagine an interface change. How much would that mess up search.java? Good answer. This, I would agree that it doesn't have very tight coupling with ArrayList. It doesn't depend on the fact, doesn't depend on any implementation details of ArrayList, or collection actually. No, ArrayList. It doesn't depend on any implementation details of it. It only depends on the collection interface. That's interface as an object-oriented programming interface, which is similar to interface for RSAC. You'll learn more about that other kind of interface in Comp 2150, object orientation. What I'm trying to say is that collection is a not quite a super type, parent type, base type, whatever, but it's like one. I want to explain object orientation without actually explaining object orientation. You can switch out ArrayList for any other subtype of collection without messing anything up. So you might say that it's kind of coupled to collection, but I'm pretty sure collection itself is only an interface, doesn't enforce any implementation details, and ArrayList is just one implementation of it. So it's not really fair to say that it's coupled to an interface. So yeah, you can switch out the data structure and the program would still work perfectly, which is a sign of low coupling. Agreed, ArrayList low, and also scanner low. Excellent response. Where do we use scanner? Yeah, I'm too rusty on file I/O in Java to really assess this, but it doesn't look that coupled. It looks like you can swap in anything that has something to handle line-by-line input, and you'll be fine. And more importantly, it doesn't depend on any details with how scanner goes line by line. I'll give you all a little bit longer, but I don't really blame you for the lack of responses. I really think that game.c should have been first in this quiz because search.java's self-contained nature kind of makes it hard to judge its coupling, cohesion, and just coupling and cohesion. Give like 5 or 10 seconds for more responses. Okay, let's move on. Now what about game.c? This one has sort of more of a objective answer, so I hope you can find it. Someone says it's very highly cohesive, perhaps. Maybe not quite that cohesive, but still cohesive. Uh-huh. Well, someone, or at least one person said it's very incohesive. I'm liking the contention here. Is this gonna end up being bimodal? That'd be messed up. So I think I'm going to leave this one here. We have what looks like a slight majority saying that it is cohesive, but some saying that it isn't. Well, I thought about it a bit harder while I was sitting down, and I think this is a bit of another trick question, but it's good to work your brain on these sort of questions because I was going to say not everything is objective in computer science, but almost nothing is objective and simple in computer science. So let's just open that up again. Am I going to have to open up yet another terminal window? Yeah, it's the simplest way of window management I could do in the constraints of a lecture. If I were actually working on this, I'd, unmaximize those windows and put them together in tabs. But this is faster. So what does game.c do? Well, it's a game. It's got players, items, rooms, and functionality to tie them all together. It also handles input, checks a bunch of conditions, does some memory management, using zones, in fact. If using zones.c wasn't enough, this is another neat usage example and will actually come into play during the third question of the third assignment. Don't worry about that right now, though. So, you're both right. It is pretty cohesive in the sense that all of the functionality fits together. It's not like we have room management, player management, and also a banking app or something built in. I don't know. No NFTs, I hope. It's all game stuff. It all fits. So it's cohesive. But remember the single responsibility principle. Do one thing and do it well. Can't comment on how well this does things, but I can say this definitely doesn't do one thing. This nearly 500 or 500-ish line file does a whole bunch of stuff, and you could tell by the struct definitions, which are also just placed there, not totally exposed to the things that are using them. If you kept working on this game, it would become unwieldy and hard to work with very fast. Whoever wrote this really should separate the different parts of the game, like the player, the rooms. What was the third struct again? Items, into separate modules. And then those modules would be cohesive. Let's just spend 2 minutes on the last bit. Try to think of what Game.C is coupled with. And in this case, it really is coupled with some stuff. And figure out whether it's tight or loose. And then once the clock strikes 1:45, you could go, I won't judge you. Do try to make an answer beforehand, though. Got about 5 seconds left before you could go. Oh, yes. Yeah, if we were to split up the modules and make them cohesive, they would be pretty darn coupled with each other. Great job. I just wanted to also mention that it's quite coupled to its dependencies, especially the curses library. That's all. Have a great long weekend, and I'll see you all for the last couple lectures of the course.